Welcome to section 2.3, prime cuts of numbers, how the prime numbers are the building blocks of all natural numbers. As always, you're going to want to pause often, take notes, retry the problems, rewatch, and rewind. So pause here. Can you write 71 as a product of two smaller numbers? So go ahead, try it out. Grab your calculators. You're going to want them for this today. And press play when you're ready to move on. So a prime number is a natural number greater than 1 if it cannot be expressed as a product of two smaller numbers. So first of all, it's got to be greater than 1. And so 1 is not prime. But if it can be expressed as two numbers multiply each other, so 6 is equal to 2 times 3, so that's not prime. But 7 can only be expressed as 1 times 7, so that is prime. No other way than itself and 1. So let's figure out all the prime numbers. So what I'm going to ask you to do now is to either find on the internet or write out all the numbers just like this, 1 through 10, all the way to 100. Make it look exactly like this for me, please. We're going to actually show how to get every single prime number. So first, what we're going to do is we're going to cross out 1 because we know 1 is not prime. Next, we're going to circle 2 because 2 is prime. The only way I can write 2 is 2 times 1. But the thing is every multiple of 2 can be divided by 2. So I'm going to go through and cross off every multiple of 2 because 4 can be written as 2, and 2 times 2, 2 times 3, 2 times 4. And what ends up happening is we're going to actually cross off like all the other even numbers. So you can cross those off one by one with the X's, or you could do kind of what I'm doing here. So look at that. We've already gotten rid of half of our numbers. All right, now let's keep going. 3 is prime because it's only 1 times 3, but now I'm going to cross off everything that is a multiple of 3. Well, 6 is already crossed off, 9. 12 is crossed off, 15. 18 is crossed off, 21. 24 is crossed off, 27. 30 is crossed off, 33, 36, 39. And I'm going to keep going, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 72, 75, 78, 81. I'm just adding 3 each time. 84, 87, 90, 93, 96, 99. Okay? 5. Go cross off all your multiples of 5. Well, we know that this section's already done, and so we can cross off this whole section here. All right, let's look at 7, all of our multiples of 7. So what are our multiples of 7? And so we keep going here. We've got 14, 28, 21, 28, 7 times 5 is 35, 7 times 6 is 42, that's even. And so I want you to pause here and continue this for the rest of the numbers. Press play when you're ready to see what's left over. And that is what your chart should look like up here. And that is what's left over. Those are our prime numbers between 1 and 100. Oops, sorry about that. So now how do you actually get the prime factorization of natural numbers? So we're going to use what I call as the birthday cake method. And what we're going to do is we want to know, well, how can we write every natural number as a product of prime numbers? So, oops, let's get that guy over. Okay, so write the following numbers as a product of prime. So first I'm going to list out all my primes at the top. Not all, but my first few. All right, and now I'm going to write the number that I'm curious about at the bottom of my birthday cake. So you might want to watch this one first before you give it a try. And I always start with the smallest prime, and I see, can I divide that prime by, and I'm going to show you my calculator here so that you can follow along, because sometimes we don't really know how to use our calculators so well. So I'm going to say, all right, 60, and you might know this already because it's even, 60 divided by 2. I put the prime number on the outside. And then the result, 60 divided by 2 is 30. That becomes the next layer in my birthday cake. And I stick with that prime until So divide by 2 until I can't use it anymore. Well, I know it's even, so you probably did too. We know that 30 is divisible by 2, and we get 30 divided by 2 gives me 15. On the outside of the cake are the primes. Now, you might know 15 is not even, but if you're not sure if it works, if you get a decimal, it doesn't work. Whoops. If you get a decimal, it doesn't work. So now we try the next prime, which is 3, and we get 5. And now you might say, oh, 5, I'm done. Don't forget, your birthday cake is not complete. 5 divided by 5 is 1 until you put a candle on the top. So this is the prime factorization. How you write a prime factorization is you say 2 times 2 times 3 times 5, or you can express it with exponents, 2 to the second power times 3 times 5. This is the prime factorization. Now, how can you always check and make sure you're right? Just multiply it. 2 times 2 times 3 times 5, 60. We can even do the same process for big numbers. Start at the bottom of the cake. I actually know that this number is even because it ends in a 0, but I don't know off the top of my head. 7350 divided by 2 gives me 3675. 3675. I know that cannot be divided by 2, so I'm going to look for 3 now. So I'm going to try to divide that by 3. I get a whole number, 12225. And I forgot my prime there. Don't forget your prime. So 12225. Let's see if that's divisible by 3. It is not. So I'm going to try my next prime, which is 5. 245. So this was divisible by 5, and I got 245. 245 looks like I can keep dividing that by 5. And I can, and I get divided by 5, and I get 49. I know that 49 is divisible by 7. Oops, I was keeping that green, sorry. 7, and don't stop there. 7 divided by 7, you're not done until you get the 1. And I made that, sorry. This is the prime factorization. 7350 can be written as 2 times 3 times 5 times 5 times 7 times 7, or 2 times 3 times 5 to the second power times 7 to the second power, and let's just double check. 2 times 3 times 5 times 5 times 7 times 7, 7350. Go ahead and give this a try here with these 4 numbers and press play when you're ready to see the solution. And there we go. So here's the question. There are infinitely many primes. That actually has been proven. Truly difficult problems can be solved. So now we ask this question, do we know all of the math? A lot of people think that math is this static, ancient formula technique, but in reality, a lot of math is still unanswered and still not even asked yet. So let's look at 2 open questions that are still not proven in math. This is called the twin prime question. The question is, are there infinitely many pairs of prime numbers that differ from one another by 2? Mathematicians have not formally proven that yet. The Goldbach question, can every positive even number greater than 2 be written as the sum of 2 primes? We don't know. So go ahead, try this out. How many twin primes can you come up to? And how many do you need to figure out until you can say that there are infinitely many? The Goldbach question, how many can you figure out? And that concludes section 2.3.